In this mini lecture, we're going to look at poles and zeros of a transfer function, define them and look at them. We're going to look at using the pole-zero map and also the final value theorem and the DC gain of a transfer function. So by definition, the poles of a dynamic system, so some transfer function that we have, that's what you could say h of s, are the values of s, the complex numbers s, where h of s goes to infinity. So as an example, consider the system h of s is equal to 1 over s plus 1, then the poles of h of s are simply the places where h of s goes to infinity, so that would be s equals minus 1. Notice that's because the limit of 1 over s plus 1 as s goes to 1 is equal to infinity. We could also look at, say, h of s is equal to 1 over s squared plus s plus 1. Then the places where s plus 1 equals 0, using the quadratic equation, we get s equals negative 0.5 plus or minus j times the square root of 3 over 2. And again, that's where the limit of 1 over s squared plus s plus 1 as s goes to minus 0.5 plus or minus j times root 3 over 2, that goes to infinity. And we can plot the poles on the s domain, real, imaginary, as and we use x's. We use a little x there and an x there. That's at minus 0.5. This would be a plus root 3 over 2, and then minus root 3 over 2, and this is the j-axis. Notice that the poles of the transfer function h are also the roots of the characteristic equation, and that's always going to be true. And that is just the denominator of the transfer function. The zeros of a transfer function are the values s, the complex values s, where the transfer function is equal to 0. Instead of infinity, it's 0. So again, by way of example, if we have, say, s plus 1 over s squared plus s plus 1, then the zeros are of, call that h of s there. The zeros of h of s is equal to the set of minus 1, because we see that if s equals minus 1, the numerator goes to 0. But notice as s goes to infinity, then I get infinity, I can divide through by s. And let me do the, and minus infinity also. So there are actually 3 zeros, and 2 of them are at infinity. Normally we don't, we're not so concerned about the zeros at infinity in terms of dynamic response, but they actually will be important when we talk about root locus. But that's further down the line. But notice the limit of s plus 1 over s squared plus s plus 1 as s goes to infinity is equal to the limit as s goes to infinity of, if I divide through by s squared, I get 1 over s plus 1 over s squared all over 1 plus 1 over s plus 1 over s squared. So those go all to 0, 0, 0. So that's equal to 0 over 1. We can also plot the zeros in the complex plane and on the real and imaginary of the j-axis. And we can plot those as the finite zeros as circles. So that's at minus 1, say. And in this case, the poles of the system would be there and there. So that's minus 0.5, and then plus root 3 over 2, and minus root 3 over 2. The finite zeros are known as the transmission zeros, because when we're at that 0, the signal is not transmitted. So it's a way of where the plant blocks the input when I'm at a 0, because the transfer function takes on the value of 0. You can think of it that way. We can use MATLAB to do all this, so let me switch over to MATLAB and show you. Of course, we can always use MATLAB to do anything, it seems like. But in this case, if we define a transfer function as, let's say, to use the example we just looked at, and so I define that using the TF command, then there's a number of commands I can call to understand what the poles and zeros of the transfer function are. I can use the PZ map of the sys, and notice what that command does is actually take the transfer function object and then go ahead and plot the poles and the zeros, the finite zeros, in the complex plane. If I put the grid on, one thing that's interesting to notice is that it's actually plotting these in a polar coordinate system, okay, and not necessarily in a Cartesian coordinate system. The other thing I can look at is I can use the command pole of the system, and that tells me what the poles are. I can use 0 of the system, and that gives me the finite zeros. And what's interesting to notice here, of course, is that the poles are the same as the roots of the characteristic equation, which is the same as the eigenvalues of the differential equation. And these zeros are doing something different, and we don't really understand at this point yet how they impact the system. We understand the response of the system in terms of stability has something to do with these poles or roots of the characteristic equation. All right, now we can look at the final value theorem, and the final value theorem says that the limit of any function of time, say y of t, as t goes to infinity. So I want to know what happens in the limit that time goes to 0 or infinity, hence the final value, is equal to the limit of s times the Laplace transformation of the function y of t, so y of s, as s goes to 0, if and only if the limit of y of t as t goes to infinity exists. All right, so this doesn't work when this limit goes off to infinity. In this case, then, y of s, just to be explicit, is the Laplace transform of y of t. The other way to think about this is that this limit will exist if and only if the poles of y of s have negative real parts. Right? If they do, this limit will exist. As an example, let's look at the DC motor speed transfer functions. So in other words, if I had the differential equations, which are tau theta m double dot of t plus theta m dot of t is equal to k times u of t, let's let u of t equal a step and a unit step function. And then for when I take the Laplace with regard to the speed, I end up with tau s theta m of s dot plus theta m dot of s is equal to k times 1 over s. And when I solve for theta m dot of s, I end up with k over s tau s plus 1. Now, if I'm interested in finding the final value of theta m dot as a function of time, the final value theorem tells me that the the limit of theta m dot of t as t goes to infinity is equal to the limit of s times k over s times tau s plus 1 as s goes to 0. So those s's cancel out, and I end up with k. So I don't have to actually solve the differential equation to find out what the final value of the solution to the differential equation would be. If I just have the frequency domain transfer function and then knowing what the input is, I can tell you what the final value is in time by looking at it in the S domain. Finally, the last thing we want to look at is what we call the DC gain. And the DC gain is defined as the ratio of the output to input after all transients have gone away due to a unit step. So this is similar to the, it's an application essentially of the final value theorem. So the DC gain of a system is to take the limit of the transfer function as t goes to infinity, or another way to say that is in the S domain, it's s, the limit of s times g of s times a unit step, 1 over s, as s goes to 0. So that really is just the limit of the transfer function as s goes to 0. So for us, with the DC motor, for say the speed transfer function, then here g of s is just k over tau s plus 1. So the DC gain is just the limit of k over tau s plus 1 as s goes to 0 is equal to k. So that's one reason this is called the motor gain constant. Notice in the previous example for the final value theorem, we got the same kind of result. That's just particularly in this example, but as long as the transfer function g of s has stable poles, then, or poles in the left half of the complex plane, then I can take this limit via the final value theorem and find the DC gain. Notice let's use another example. If I have the mass on a spring with damping, then that transfer function we've found to be omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And if I look at the limit of g of s as s goes to 0, I end up with omega n squared all over 0 squared plus 2 zeta omega n 0 plus omega n squared, and that equals 1. So a mass on a spring with damping has a DC gain of 1 if it's scaled properly.